Hi everybody, welcome to week 4. Apologies for the fact that someone's punched me in the face. Just have epic hay fever today apparently. That's what's eating. So apologies for cancelling last week. Completely forgot. It was Mother's Day. And then, yeah, anyway. So we've covered hydrocarbons, isomers, functional groups, a little bit of naming. So now we're going to get into the nitty-gritty stuff. I'm actually moving through this probably twice as fast as I normally would. Last year, the teaching was terrible because of COVID, but the teachers seem to be on top of it a bit more this year. So I'm going to get through as much content as possible, and then we can spend as much time as possible doing exam type questions. So this week will be fairly hectic. There'll be quite a bit of information. It's not everything you need to know, but it'll give you a good grounding for when your teacher goes through it. Some of you might have already gone through some of this in class. But we're going to spend 1 minute, everybody, writing down what the 3 intermolecular forces are and what kind of bonding produces them. Because every week we will go over the intermolecular forces again and again and again and again. Because they underpin everything in organic chemistry. And you probably hate me, but I'm okay with it. So 1 minute. Thousand steps. All right, 3 intermolecular forces. We have dispersion forces. Am I going over it each week? We'll get faster and faster and faster. We then have dipole-dipole. We have hydrogen. And all of this is because of the difference or lack thereof difference of electronegativity. Dispersion forces, we have carbon to hydrogen bonds. Difference is 0.4, so it's a non-polar molecule. The hydrocarbons have dispersion forces. The only ones. I mean, all of the others have dispersion forces as well as dipole-dipole hydrogen. Dipole-dipole, we have carbon double bound to oxygen. Difference between carbon and oxygen is 0.8, creates a polar molecule. Oxygen also has 2 non-bound electrons, which increases the polarity. Hydrogen is when we have hydrogen bound to oxygen, nitrogen, or fluorine. We also get it when we have carbon bound to a halogen. Oh no, never mind me. Carbon to halogen is a slight dipole bond. So, dispersion forces on the hydrocarbons. Dipole-dipole are your esters, ketones, and aldehydes. Hydrogens, amine, amide, carboxylic acid, and alcohols. All right, so we're going to look at the reactivity of the molecule and how we can actually test for it. So what we'll learn about in term 3 is some more complex methods of determining organic compounds. So NMR, or nuclear magnetic resonance imaging, X-ray crystallography, blah, 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 as well as mass spectrometry, so on and so forth. But the simplest tests we can do, so for carboxylic acid, anyone guess what kind of test we could conduct to see if we have a carboxylic acid? all in the name. This was on last year's exam too. They don't always put the complicated questions in there. So we could use pH. pH scale, 0 to 14. Acids are going to be 0 to 7. If you have an organic compound that you don't know what it is, and you test it, and it's pH 4, you know it's an acid. Because carboxylic acids donate H+ into the solution. So that hydrogen on the end is donated into the solution. And I'm not going to spend much time on this at all, because there's only a few of them that have really simple tests. We can test for the presence of amines, again, through our pH test. On the end of the amine molecule, nitrogen has a lone pair of electrons. So, I don't know if you can see that in the reflection. Lone pair of electrons. Now, I say the polarity of the molecules in organic chemistry tell you everything. We have a hydrogen bond. When you add an amine into a solution that is acidic, you'll get another bond using this lone pair. So it accepts the proton or the hydrogen from the acid. Now, everything you learn about acids in term 1 said that bases are OH minus, which is almost always true. But a base is a base because it can accept H+ to become something else. So you add an acid and a base together, you get water. If you take NH2, which is on the end of an amine molecule, and you put it into an acidic solution, it will produce NH3+. So although it's not OH minus, like you learned about in term 1 and in grade 11 and probably grade 10, 9, 8, in organic chemistry, it's anything that can accept a H+. If you've got an unknown organic compound, you test its pH and it's basic or 7 to 14, you know that you've got an amine, an amine. Now, I want everybody that has 1 minute to explain the 3 different alcohols, primary, secondary, and tertiary. And if you want to, you can help explain it in the chat. So we have primary. If you can hear craziness, that's just matter. Although it's 3 now, so still crazy. Okay, so primary alcohol is an alcohol that's attached on the end, or the carbon that it's directly attached to is only attached to one other carbon, hence primary. Or that's another symbol you'll see for. Just realized what a terrible draw that is. Secondary. And this, once again, will blow your mind. In the secondary alcohol, the carbon that the hydroxyl group is coming off is directly attached to two other carbons. Oh my gosh. Who would have thought? How many carbons are attached in a tertiary carbon? Any ideas? In a tertiary alcohol. It's doped up on so many antihistamines right now. I don't know what weighs up. So tertiary alcohol. I know, mind blowing. It's attached to three other carbons. Now we can test for this. I don't know if they're still doing it anymore. They did it in 2019. Obviously didn't do it last year because of COVID. But you can do a test. A molecule called potassium permanganate. Potassium permanganate. And potassium permanganate is an oxidizing agent. Well, what it does in organic chemistry is it adds a double bond. So oxidizing agents add a double bond. Or oxidizing goes from single to double. If it was a reducing agent, we would lose the bond. We would go from a double bond back to a single bond. Everybody keep it up. So if we added this potassium permanganate to a primary alcohol, what we would end up with is actually, and I'll draw the molecule properly. When we add it, when we add potassium permanganate or a strong oxidizing agent, it adds a double bond onto the end and produces carboxylic acid from a primary alcohol. Or it goes from green, I'll show you a picture, goes from yellow to green. So starts as yellow, primary alcohols will form carboxylic acid. The secondary alcohol will react, it will reduce this bond and produce a ketone. We're definitely not going to get any exam questions on today, but if we get through all of this, all next week, we'll be doing pretty much a little bit of revision, and then we will just attack like 45 minutes worth of exam questions and problem solving questions, because this is the vast majority of term 3's work done in 4 weeks. So. But a tertiary alcohol, so effectively what this potassium permanganate does is it attacks the carbon atom. But because a tertiary alcohol, the carbon atom here is completely surrounded by other carbon atoms. And there's no hydrogens to kick off. It is unaffected by the potassium permanganate. Now, depending on whether they've altered the study guide for this year, which I don't think they have, it all still looks the same, you will probably do this, or at least have this explained to you and sort of even a video of it done, which kind of gives you more of a visual effect. I'll draw that. Give everyone a minute to write this down. So sometimes you'll see a 1, 2, or 3 to demonstrate primary, secondary, and tertiary. All right. So I don't want to spend too much time you guys drawing. I'll send you a recording. My computer died. Well, it's still dying. But I managed to get the recording off after it died. So I do apologize for the recording being quite late for week 3. But I will get this recording up ASAP. All right. We can test for the presence of alkenes by this weird method. So we all know what an alkene looks like. We all know that's an alkene. We can, everyone knows what bromine looks like, right? It's this horrible dark brown red. If we add an alkene plus bromine, and we will go, why did I written with an E? It might be just having a mental breakdown. So if we add bromine to an alkene, and we'll go through, there's 11 reactions, which I don't know if we'll get through them all, but we actually produce a halo alkane. Now this will make more sense after this session. I never would understand why they teach it this way, but you know, YOLO. So we end up an alkene plus bromine equals a halo alkane. So if we were to add bromine to an alkene solution, we would not see any color change. It would stay clear. Because the bromine, when it's attached to the halo alkane, does not have any color. So if you take bromine, you add it to an unknown organic compound or organic solution, and if it goes clear, you know that it's an alkene because the bromine is reacting. The bromine is a horrible brown red color. Absolutely horrible brown red color. You add it to an alkene and you get a colorless solution. If it's anything else, the solution will stay that horrible dark brown red color. So we can test for the presence of alkenes by adding bromine. If we get a colorless solution, we know that the starting molecule was an alkene. Term 3 will go through NMR spectroscopy, mass spectroscopy, all of those things which are more complicated ways to determine the presence of an organic compound. But that's term 3. Term 3's problem. All right. So, now, your teachers have probably taken you through, with the hydrocarbons, some substitution. The substitution reactions, reduction reactions, addition, and elimination. So we can make any of the organic compounds from already existing compounds. So, and there's 11 of these. I hope your brains are ready because it's quite dry. Black pen working today? No. All right. So, reaction number 1. 11 of these, hang tight, it's a hell of a ride. We start with an alkane. So we have our alkane here. If we add chloride, here's a hint. When you get these, they'll ask you what plus what equals chloroethane. Anytime you're writing a halogen, they do not exist by themselves. They exist as diatomic molecules because they're so reactive. So we take our alkane, we add Cl2. The Cl2 is more reactive than the hydrogen. So RIP to the hydrogen. The hydrogen is kicked off and the chlorine takes its place. But remember, there's one chlorine left open. So if we add chlorine to an alkane, we get a halo alkane. I know, shocking, right? You add a halogen and an alkane, you get a halo alkane. But we also get HCl, because this hydrogen has been kicked off, and this one chlorine that's left from Cl2 will give us a halo alkane and hydrochloric acid. That's reaction number 1. Reaction number 2 is exactly the same. Well, I mean, it's not exactly the same. We take a halo alkane and still a little bit crazy, so we'll add chlorine again. And I'm actually going to send, I've got a wicked PowerPoint for this, so I'll send that out with the recording, and it's a little bit more depth. So we add a halo alkane, and then we add chlorine again. We get, the hydrogen gets kicked off because it's less reactive than the chlorine. We get a dihalo. So the halo alkane, or reaction number 2, halo alkane plus another halogen, could be chlorine, it could be anything. Anything from group 7. We get a dihalo alkane. And then I'm not going to keep going, but we can continue this. And we also, again, have HCl as a byproduct, hydrochloric acid. Is that making sense to everybody so far? I'll say, okay, so. Everybody freaks out about these. The substitution reaction. So whatever you add to that is going to replace one of the hydrogens. It's not, I won't say it's not that difficult because I mean, it's easy for me to say. But the idea is that it's not, when you're doing substitution, whatever you're adding will kick off a hydrogen in this situation. All right. So reaction number 3. It is still just a substitution reaction, but they're a little bit more complicated. And I'm pretty sure I haven't actually explained this function. No, I must. So now we're going all the way back to our alkane. So remember, add something, it's going to kick off the hydrogen. So if we add or cyanide, because why not? Why not take a deadly poison and mix it with an explosive gas? Crazy. So it's a substitution reaction. So one of these hydrogens is not going to make it, unfortunately. So hydrogen gets kicked off. Oh no! C N gets added on to the end. Now, if you ever see carbon bound to nitrogen and you don't put a triple bond, just picture me giving you a disapproving look. So carbon to nitrogen must be a triple bond. And we call that a nitrile. You don't really need to know much about nitriles because, I mean, we make gloves out of them outside. So again, substitution reaction. We add Cn minus. It's going to kick off a hydrogen and go on. So we can make an amine. So now we have a slightly different start. So now we go from an amine, sorry, a haloalkane to an amine. Now I want you to tattoo this onto your forehead backwards because you need to know this molecule and you need to know it well. If we add NH3 or ammonia, now if you understand your functional groups, you shouldn't have a problem with it. There's only one functional group that just has nitrogen and hydrogen. What is it? It's an amine. So the amine group It's more reactive than the chlorine. So we add NH3. Chlorine gets kicked off. Oh, no. We add N and then 2 hydrogens. We've then got 1 more hydrogen left. So we end up with an amine and hydrochloric acid again as our byproduct. There's one thing I forgot in the beginning for reactions 1 and 2. They have to be done in the presence of UV light because UV light will break the bonds between them. But again, I'll send you the slides with this. All right, so I think we've got 1 more substitution reaction to go. I'm pretty sure it is a haloalkane to an alcohol. So again, starting with chlorine. And like I said, if you understand the functional groups, this should be quite easy. We take a haloalkane. It's a substitution reaction. Oh my gosh. We add OH minus, usually in the form of sodium hydroxide. Well, as you know it, drain cleaner. Chlorine gets kicked off. We know that when we add sodium hydroxide to a solution, we end up with Na plus and OH minus. OH minus goes, oh, I'm more reactive than chlorine. Thank you. And we get a chlorine molecule and Na plus left over. So it's a substitution reaction. We've got chlorine on the end. We have OH minus. We know that OH minus is an alcohol. So we end up with an alcohol plus sodium chloride. So we can produce an alcohol from a haloalkane by a substitution reaction with sodium hydroxide. And everybody freaks out about this. I mean, there's a lot to know. But if you understand how all of this works, if you understand the functional groups, it should all make sense. And we're going to, next week, we are just going to practice these equations and these reactions until one of us cries, or all of us cry. I don't really know. So now we are looking at the addition reactions. And now you're probably saying, how can we do addition reactions? Well, we add a small molecule. We add a molecule. Before we were substituting for something else. Now we're adding a molecule. So we start with an alkene. So we start with a carbon, double bond. What we want to do, RIP piece, the double bond. We'll do that by adding, for the first one, if we add Cl2, it doesn't like the double bond. So it effectively attacks it and breaks it. So now we have and then chlorine attaches underneath the carbon and gives us a dihaloalkane. A lot of these compounds are not really naturally occurring at all. So we have to make them from feedstock, from your oil. So all of our alkenes, alkanes, they come from crude oil and natural gas. So we can make all of these nice fancy. This one is called dichloromethane because there's two chlorine. So dichloroethane. Because there's two carbons and there's two chlorine. And that is a really important industrial solvent. And it's also very important in the pharmaceutical industry. But it doesn't exist naturally. So we start with simple compounds and we can make them more and more complicated. So this is an addition reaction, an alkene to a dihaloalkane. And I want you guys to study these, and I'll send the slides as well afterwards, because next week we are just going to be doing questions on these reactions. We can go from an alkene to an alcohol. So we add sodium hydroxide. Some of these reactions require heat or a catalyst or something similar. Actually, this is a different one. Sorry, this is not sodium hydroxide. This one is, if we take an alkene, we add water, we add hydrogen phosphate, and we heat it to 300 degrees Celsius. We can produce, go from an alkene to an alcohol. So what this does is it splits this molecule into OH minus and H plus. So we heat up the water in the presence of this H3PO4, or hydrogen phosphate, at 300 degrees Celsius. What happens is the bonds break. The H plus from the water goes here. We get single bond forming, and then the OH is added on. Go through these quite quickly, but we will go through them next week with the exam practice questions and really nail. All right, so back to our alkene. Back to our alkene. Now we can also go from an alkene to just a haloalkane. So what we can do is we add hydrochloric acid, HCl. We know it's an addition reaction, so we RIP the double bond. This H goes here. The Cl attaches onto that carbon and gives us a haloalkane. Now we're only going to go through 10 reactions, I think, because the other one is a polymerization reaction, which I think we'll leave until maybe the next one, maybe next time. So we take an alkene, we add, this is called a hydrogen halide, very creative. Hydrogen attached to a halogen, to call it a hydrogen halide. The double bond breaks. Hey, there's a hydrogen attaches on, chlorine attaches on, and we get a halo alkene. So the next two reactions are probably the most annoying. We get a reduction. We can have a reduction reaction, and you'll never guess what that's the opposite of. An addition. It's the opposite of an addition reaction. So we have a reduction reaction. I want everyone to take a minute to think if an addition reaction is to break the double bond. What are we doing with an elimination, with a reduction reaction? Sorry, elimination, not reduction. Why do I keep going reduction? It's elimination. So elimination reaction is just the opposite of the addition. So we are now rebuilding the carbon-to-carbon double bond. So we start with a halo alkene. Let's say Cl. So now we're going to go from halo alkane to an alkene. It seems like I'm going through this quickly. It's because I am. But we will nail the concept next week, and I'll upload it. I'll upload it right now after this and send it with the slide notes. Hopefully, by next week, you're all geniuses. So what happens is we add, and this is, so we add heat. We add sodium hydroxide, our favorite chemical. And that breaks off the HCl and reinstates the double bond. So NaOH breaks up into Na plus and OH minus. We've got hydrogen left over, which will bond with the OH minus to produce H2O. The chlorine will bind with the Na plus, and we'll get NaCl. So the elimination reaction, we're eliminating molecules to reinstate the double bond. So we can go from a halo alkane to an alkene. So our last one is going from an alkane to an alkene. Sorry, alkene to alkane. This isn't very common. So we start with an alkene. we add hydrogen. This doesn't just happen. There has to be something driving it. Whether if you're adding it to something that's very reactive, whether you add UV light, whether you add heat, sometimes we have to add a catalyst that breaks the double bond for us, and then we end up back at an alkane. That was a lot of information to chuck at you guys. But what I'm hoping is if I send you the slides as well, and you can do some of your own reading, by the time we get to doing the exam questions next week, you guys will be ready for it. I'm actually going to make sure the recording goes up straight away. So there are 10 reactions and the pathways that they follow. Have a read through the slides. Your teacher will go through it as well. But just remember to be logical. If it's a substitution reaction, you're replacing one functional group with another. Just look at what's being reacted. Remember your functional groups and remember the polarity. Next week's session will just be on the first 4 weeks, and we'll do a little bit of revision in the beginning. Then we'll do practice exam questions for probably 50 minutes. And that should cement everything before we try to move forward into esterification, proteins, polymers, so on and so forth. So the first 4 weeks is going over the basic content that's required. We'll then spend week 5 just doing exam questions. I will see you guys next week. Someone post something in the chat. Oh. Sorry, I didn't realize, I didn't see the chat. So, alkene to alcohol reaction would be hydrogen phosphate. Hydrogen phosphate, water, and 300 degrees Celsius, and a load of pressure. H3PO4 is the catalyst. It also supplies a hydrogen. But it's mostly the heat and pressure. They actually call that steam reforming. You're looking for the technical term. But we'll go through everything in great detail next week when we do the practice exam questions. Why things happen, why they go certain places. I just wanted to give you guys an overview. So next week I didn't try and break your brain with the questions. I will see all you guys next week. I'll see some of you in the week.